Today I'm going to be going over the relationships between momentum, impulse, a force exerted on an object, and the time of interaction. Then we're going to be going over how to use the selective routine and solve for a problem using the impulse momentum theorem. So the first thing for today's agenda is we're going to talk about what is momentum and impulse. Momentum is defined as the product of mass and velocity, giving us our first equation, P equals mv. It's also a measurement of how much mass is in how much motion at a certain time. An easy way to think of momentum is how much would it hurt if that object came and hit you, and that would be the momentum. So if an object with a higher mass came and hit you with a medium velocity, that would hurt because it has some velocity and it's hitting you with a lot of weight. And if an object with a medium mass came and hit you with a large velocity, it would still hurt because it's coming and hitting you very hard, even though it doesn't weigh that much. So moving on. Next, we're going to talk about impulse. And impulse is defined as the change in momentum. So if we can use the symbol J for impulse, it would just be equal to delta P. Impulse can also be thought of as when a constant force exerted on an object for a certain period of time. So like if you had a baseball and you threw it and there was a guy with a bat and he's swinging his bat, the time that the bat is hitting the ball, that would be the time that it's being exerted, and the force would be obviously the force the bat exerts on the ball. And so the impulse would change its momentum, and therefore it would go in a different direction with a different velocity, and that would be the impulse. So that we can get our third equation, J equals F delta T. The force being that constant force you're talking about with the bat, and the time being the time period that the bat is in contact with the ball. I'll go on to prove this equation later on. Now that we understand what momentum and impulse are, let's go over the mathematical relationship between them using Newton's second law. Okay. So to prove our impulse equation here, we're going to use Newton's second law of motion, that F, the force exerted on an object, is equal to the mass multiplied by the acceleration. And in doing this, we're going to also discover some key relationships that are necessary for solving problems related to impulse and momentum. Since we know P equals mv and F equals ma, we can also say delta P is equal to m delta v. Given this, if we divide both sides by delta t, which is the time of interaction between the object and the force, we'll get delta P over T equal to M, and remember this right here is actually equal to A, given by our initial kinematic equations. So we get MA, and MA over here is equal to F. So we get delta P over delta T is equal to F. Finally, we multiply by delta T on both sides, and you get delta P is equal to F delta T. Or no, yeah, T. Given that J equals to delta P, we're just going to substitute delta P for J, and we'll get J equals F delta T. Now that we've gone over the mathematical relationship between momentum and impulse using Newton's second law, let's go over the selection of routines needed to solve for a problem using the impulse-momentum theorem. Okay, so let's use these relationships here to establish our key calculations needed to define the impulse-momentum theorem. So let's use first J equals F delta T. So we're just going to put F delta T on this side. Is equal to delta P because delta P is equal to J. And then that delta P is equal to M delta V. Okay, since they're both equal to delta P, we can just say they're equal to each other. So we'll get to F delta T equals M delta V. Delta V we know will be the difference in the initial and final velocities. So let's put that in here also now. F delta T is equal to mvf, and this is of the object on which the impulse would be acting upon. minus mvi. Oops. So this is going to be our impulse momentum theorem. All right. So now that we've gone over the concept and the theorem for impulse and momentum, let's do an example problem and apply this. Okay, so let's try an example problem now. Here we have a problem with a baseball of 0.14 kilograms mass being thrown at a batter. The ball is thrown with an initial velocity of negative 38 meters per second, and it's hit the final velocity of 58 meters per second. The reason this initial velocity is negative is because we're taking the direction in which the ball goes as final velocity outwards from the batter as positive. So initial velocity is negative. So to solve this problem, let's use our momentum impulse theorem. So that one's J equals m vf minus vi. And so from here we can just substitute in for our variables. So we're going to J equals 0.14 times 58 minus negative 38. Another quick simplification. So 58 plus 38, which means J is equal to 0.14 times 96. And that's going to end up at around 13.4 Newton seconds. Newton seconds is the unit of measurement for impulse and momentum. We get that from multiplying force times time. Alright, now let's go on to part B. Part B is that we're given a time of 1.6 times 10 raised to negative 3 seconds, and we have to solve for the average force. So here we're going to use our equation that J is equal to F delta T. So F is equal to J over delta T. And that means that F is going to be equal to what we have in our previous question, 13.4, over the time 1.6 times 10 raised to negative 3. So F is going to be equal to around 8,400 newtons. Newtons being the unit of measurement for force. Okay, so just to go on a brief recap of what we've learned today, the first thing was we went over what momentum is, and that it's the mass, it's a multiplication of the mass and velocity. We went over impulse as well, and then we used Newton's second law, F equals ma, and we solved for an impulse equation, or derived it, and that's J equals F delta T. Finally, we used our impulse and momentum equations to derive the impulse momentum theorem, which is F delta T equals mvf minus mv1. In the end, we used this and these two equations to solve a problem. Thank you for watching.